Today I'm going to talk about something a little bit different, I guess, for our group. I'm going to primarily talk about an ERP study that I conducted as part of my thesis. But in order to explain that well, I want to sort of touch on the general background to the face processing literature, the research rationale for my thesis, and very, very briefly, the key finding from the study that preceded my ERP study, which was a study of general recognition theory. I want to provide a bit of an introduction to ERP because when I first started reading about it, I really didn't know that much about it, and I think it's really helpful to go back to some of the basics to understand the results later on. I'll go through the details of the experiment, key findings, and future research using ERP that I plan to do now. Okay, so there's very sorts of basics behind face processing or configural processing is that upright faces are thought to be processed as wholes and inverted faces are thought to be processed as parts, with the configural information between features in a face being of importance to upright face processing. And there's lots of empirical signatures that are seen across multiple tasks that support this. So the inversion effect, where faces are disproportionately affected by inversion compared to other objects that have a single orientation. Whole and part studies with faces that show facial features that are easier to identify in the whole face context rather than in isolation. The composite face effect, where people are slower and less accurate at identifying parts of the face when it is aligned rather than misaligned, because the two halves in alignment are thought to interfere with each other, making them difficult to identify. And the Thatcher illusion, in which features of a face are Thatcherized by turned upside down relative to the context. The upright Thatcherized face looks grotesque, and as it's orientated away from the upright, the grotesque appearance disappeared, which is attributed to recognising a distortion of the configural information in the upright faces, which you don't do with the inverted faces. So there are some really fundamental issues with the face processing literature, and I guess the key one is that there are still uncertainties in explaining how these empirical signatures are actually generated. What is configural processing? What is the nature of configurality? And to understand this, you have to readdress hypotheses and assumptions or theories behind how configural processing works, which is assumed to be a perceptual, face processing is assumed to be perceptual in nature, using formal tests that address the assumptions and hypotheses rather than theories. And an appropriate method to do this is general recognition theory, which is a multi-dimensional version of signal detection theory. So I'm not going to go into detail about signal detection theory, but the key point is signal detection analysis allows you to look at perceptual and decisional measures of the data. So general recognition theory represents stimuli as multivariate probability distributions. So here we have a situation where we have 4 stimuli represented as 2 different dimensions, which here are the eyes and mouth in a face, each with 2 levels, so upright and inverted features. So this is a Thatcher illusion as an example. And it's really important that the studies are set up in this way, which we call a complete factorial design for the later analysis. And the figure on the far side there is just sort of a view from the top cut across an arbitrary plane representing each of the bivariate distributions. So dimensional interactions in these multi-dimensional stimuli can be characterised as either perceptual or decisional factors, but instead of like signal detection theory where there are only 2 measures, in this instance there are 3. So there are 3 types of violation in general recognition theory, and the first of these is a violation of perceptual independence, where a correlation exists in a bivariate distribution. A violation of perceptual separability, where there's a shift in the relative position of the bivariate distribution, or a violation of decisional separability, where there's a shift in the response criterion across levels of a dimension. So the important point to take from this, there are three different measures, and two of them refer to perceptual components, constructs, and one of them is a decisional construct. And behavioural effects associated with configural processing can be theoretically represented by any of these three violations of any of these three constructs, but it's important that the theories in the literature that exist for configural processing would expect a perceptual component underlying configurality, and a violation of PI would be considered to be the most appropriate for that, because the interaction would be within a single stimulus, so within a single phase. A violation of decisional separability could still produce behavioural data consistent with configurality, but it would be at odds with the hypotheses that exist for a lot of these theories. So there have been phase processing tasks that have used general recognition theory to examine the nature of configurality. They've looked at sizing manipulations, the composite phase effect, and the factor illusion. And all of these tasks found evidence for decisional sources of configurality, and none of them found evidence for this violation of PI, which I've just explained would be the strongest evidence supporting previous theories. So it's like the construct validity, not finding it means a lot of people are they're not very happy about this recent research. But all of the studies have used a particular kind of analysis for general recognition theory. So my first study implicated these three tasks within the same study. We were examining evidence for configural processing across the three tasks, looking for replications of behavioural effects, or also orientation-specific violations from the GRT constructs. We were going to look for the underlying similarities and differences across the tasks, and we were going to compare two different types of analysis to GRT. The type of analysis that was used in the three previous studies, which is a marginal analysis, and a new type of analysis that Tammy helped develop, called the ProNet analysis. And this is because the previous analysis that was used was shown to be conservative in finding these violations. So it's not really best test of whether they're there. So we're using a more appropriate analysis, but it was the first time it's been used in these types of studies. So that's our Frontiers paper. So we did complete 3 tasks in this study, but I'm only going to focus on one of them, which is our factor illusion task, in which participants had to make 2 responses to identify whether the eyes were a normal orientation or an odd orientation, so upside down, and whether the mouth was a normal orientation or an odd orientation. And just looking at the GRT findings from this study, using our 2 methods of analysis, so the green colours for marginals and purple ones for ProNets, which was the new method, we can see that again, no violations of perceptual independence were found with the previous method. But with our new ProNet method, we do find them. And across the other 2 measures, we find evidence for violations of perceptual separability in the upright version of this task. Sorry, I should have said we use upright and inverted faces with these manipulations. Mostly violations of the S for the upright stimuli, and mostly violations of the S for the inverted stimuli. Because we use this slightly different analysis for GRT, we're able to look at the correlation values as well. So looking into, we found violations of PI across upright and inverted versions of the task. When we look at the upright version of the task, which is on the left here, 1 is upright, upright and 2 is inverted, so it's eyes along the x-axis, mouth on the y-axis. We can see a positive correlation exists for the typical upright face, and negative correlations exist when only one of the features is factorized, and no correlations exist in a fully factorized face, which might be a bit...
can you explain what correlations are? What is it that's correlated?
The features, so this goes back to the sort of the distribution, which is correlation between the different dimensions. Okay. So there's the analysis estimates the underlying correlation in the distribution. So we measure many trials
So I mean, we'll go back to your slide, 3 or 4 back. That one, right? So A1 and A2 there would be something like.
Eyes upright, eyes inverted.
Yeah, and then B would be mouth upright, mouth inverted. So the variables there are eyes or mouth, is that right? And then.
The levels are eyes or inverted.
Yeah, and then the correlations so go back to your data now. So you're saying that there's a correlation in that bottom left quadrant on the in the left graph. There's a correlation on the bottom left quadrant, and then is the 2 on the upper left and the bottom right. Is that? And then there's not 1 in the top right.
So the point to take from this is that there is evidence for a change in the type of correlations with factorisation. So with no factorisation, we have a correlation. The correlation changes with only one feature. There's no correlation in the fully factorised condition for the upright faces. So there's something interesting about a level of factorisation, which is not something that's often investigated. It's usually just a fully factorised face or a normal typical face.
So what are the units on the axis?
I think they're kind of arbitrary ones. So this where the correlation is just -1.
So the bottom left distribution is centred at 0, 0, and then the others are just relative positions of d prime and the distance between the distributions.
How would you mark the person's responses? So whether they got something right or wrong, and then you're looking at the correlation between whether they got it right or wrong with faces and with mouths, is that right?
So they don't have to respond whether there's faces or not, because there's only faces. So
and then mouths and eyes as well.
Okay, so with signal detection, you're interested in all kinds of responses, so not only the ones you get right, but how you get it wrong as well. But signal detection is only between 2 distributions. So you just have a measure of how the distributions separate, which is your perceptual measure, and then where you choose to respond, which is your decisional measure. But because you've got multi-dimensions now, you have a third measure, which is how those 2 distributions are statistically related, because you're making 2 responses to everything you see. Does that help?
Yeah, got it.
But when they make the response, how do they... So imagine I'm doing this task, right, and you show me something, and I have to press probably one button to say yes or no in relation to one of your dimensions, and another one. Is there any rule on which one they've got to do first, or is it just completely free?
Yeah, so it counterbalance. So in half the task they do, they'll be responding to one first and half to another, so it blocks.
And
so I mean, this task had thousands of trials, so and each time they came back for a new session, it was swapped to balance for that.
And I've got another question. So I can see that on that left graph, I can see exactly what you've described, which is like a correlation that way in the bottom left, and then 2 correlations that way, and then nothing at all on the top right. But what I don't understand is what that means in terms of them making the decision. What does it mean to get a positive correlation like that when you've got 2 where your eyes and your mouth are upright, then to have a negative one?
Aside from the positive or negative, it just means you're using, it's kind of like saying you're using configurality for that face, you're using interactions between parts. About it being positive or negative, I don't think I can really explain that, but the fundamental thing is you predict it to be in the fully factorised condition, you predict it to be larger there, if anywhere, and the fact that we don't find it, but we find it in the others, is that we find quite interesting, which is at odds with, again, at odds with theories and hypotheses. Okay. So just the key findings from that study, that we do find markers of whole face processing in the task, and from GRT we find evidence for all 3 violations when we use these factorised stimuli. We find something fairly interesting about the type of correlations and the level of factorisation. So, moving forward to my ERP experiment, we're interested in finding some sort of complementary evidence for finding different sources of configurality, because we've shown evidence now from perceptual and decision sources of configurality in these previous tasks. Of the 3 tasks we explored, factor illusion was the only one to show all 3 violations reliably. And in ERP studies of the factor illusion, the level of factorization hasn't previously been explored, so we thought it might be.
Sorry, by level of factorisation, do
You
you mean
mean
whether the
one
eyes
feature
or the mouth or both?
Yeah.
Okay.
So whether there's typical, just one feature factorised or both.
Right.
So we were looking to find markers of configurality using the ERP technique. And our theoretical question is there any evidence for more than one source of configurality in the ERP trace? So before I go into the details of the study, I thought I'd just give some sort of key points about the ERP technique. So EEG is measuring electrical activity in the human brain. We look at the change in potential from different points on the scalp, amplify the signal, and record using electrodes. The ERP is the neural responses associated with specific events. And recording this type of the electrical brain activity is related to the principles of electricity. So I've got a little diagram on the side just to remind us all of our GCSE physics. So voltage is the potential or the pressure for current to pass from one point to another. The current is the amount of charged electrons that can pass by a given point in a specific amount of time, and resistance is the ability of the material to prevent the current passing through. So this is important for recording EEG because we are interested in plotting the voltage across the scalp. The current in this case is the ions moving across membranes. We want to keep our resistance as low as possible to get the best recording of that change in voltage. We call the resistance impedance in ERP recording. And to reduce impedance, we exfoliate the skin at each site of the electrode recording to reduce, to increase conductance to get the best signal. And there's lots of different sources of noise in the recording, so this means that the testing situation for ERP and EEG studies is just really strict. We have to record a lot of things. Eye movements and blinks will disrupt the recording. Any kind of tension, so if you're uncomfortable, if you're too hot or too cold, if your hair is dirty, if there's electrical equipment in the room, so we've got to make sure that in the testing room there's as little in there as possible. Sneezing, yawning, coughing, anything like that. Also, other sources such as like caffeine, or if you're a smoker, the impact of nicotine, all of these sorts of things. And this is something that Linnea talked about last week, but the opposite for MG. So ERP has very high temporal resolution at a cost to the spatial resolution. So for my study, we've got we get a sample every 2 milliseconds, but we only have 60 points of reference on the scalp. Pre-processing is what's the stage before analysis where you have to clean up your data. I've talked about all these sources of noise. It looks very messy, and there's a lot we have to do to get good quality data and remove all the artifacts. And because of this, you require twice as many trials as you need because you'll lose about half of them in any study. So this is just an example of an EEG recording. The bottom is frontal sites moving to posterior sites. And this is what happens when someone blinks. You get a massive deflection at the front, and you still see the deflection at the rear. So we need to know when people are blinking, so we have to record the electrodes above and below the eye to record the muscle movement and correct for it later. Some people choose to eliminate all trials when people blink and encourage the participants to blink as little as possible. But we figure that causes like an artificial testing experiment. It's not something people can maintain if they're going to be in the lab for an hour. Naming of components, there's some inconsistency for this in the literature. So very simply, P is for positive and it's for negative. And the number either refers to the order of the component or the latency of the component which is just the N1, the first negative potential, but because of the specific latency at which it occurs in the face, the literature has adopted N170 as the term it will always use. Whereas there are some other occasions where terms are just used interchangeably depending on style. So P1 and P100 mean the same thing. It's the first positive component, but it just happens to occur 100 milliseconds, and people can use either, even if it's not in a specific area of research. An epoch is the time window in which to examine components of ERP, and this graph here is an ERP recorded at a particular electrode, and for peak detection, which is the kind of analysis I'll be using, we're interested in the amplitude and the latency of every component. Often you'll see graphs where voltage is plotted negative up, and I've looked into it. There doesn't seem to be a really good reason why people started doing it this way, but it's split about half and half. Some people do it this way, some people plot it with positive up like all mathematicians would, and never been able to standardise it. So either way is acceptable, and labs tend to just all do it the same way, and possibly journals as well. But either is fine, and I'll be plotting all mine positive up. So in terms of ERP components, there's a vast amount of literature on the N170 component in relation to face processing. And the N170 has been shown to be larger to faces than objects, larger and delayed with inverted faces compared to upright faces, and it's shown to be larger in the right hemisphere, which is consistent with a lot of imaging studies on face processing in the FFA. The P2 is a component that's been shown to be sensitive to face structure with larger amplitudes in faces that have had spacing compared to featural manipulations, larger to faces that have had contrast reversal relative to the faces, and reduced amplitude in relation to atypical faces that have been stretched compared to typical faces. So both of those components are early visual components that are listed in the occipital temporal areas of the brain. The P3B is a component that's listed in the central parietal area, and recent research suggests it's related to a response preparation or a monitoring process of some sort of mediator between after perceptual components and before a response is made. And this component has been shown to be larger to faces than objects, and especially large to threatening faces. The visual P1 is a component that's often reported in face processing studies, but recent research has shown that because the P1 is very sensitive to low level visual features, when you control your stimuli really well, there aren't actually any face specific effects that are taken out, suggesting that any P1 effects in previous studies have all arisen because of poor control over the stimuli. So this will be important for next time.
Well, can you just, could we go back one? So, can you put a time course on the P2, P3? The P1, I think, it was an N1 that you said was about 170, right?
Yeah.
So what's the P2 time course?
For mine, it's about 240 milliseconds.
What do you mean for yours?
So it would depend on the kind of study you look into. So P1 is first, then N1, then
Oh, I see. Right, you've got them all up there. Are those times about right? What I'm really
roughly,
querying.
Yeah, roughly. But they will vary slightly depending on what you see or what you hear or the sort of testing scenario you're in. Okay, so very specifically for the Thatcher illusion, there have been a few studies that have explored the Thatcher illusion with ERP, and the consensus is that amplitude reduces with Thatcherization at the N170, that Thatcherization delays the N170 and the P2, and that Thatcherization reduces the amplitude of the P2 for upright faces, but not, and the difference between upright and inverted face amplitude reduces with orientation. So when the faces are inverted, there's no difference between typical and Thatcherized faces. The consensus on these few studies is that there aren't any effects at P1, but the P3B has not been explored in these studies with Thatcherization before. So our research aims were to examine evidence for effective inversion and factorization on these 4 components, to examine whether the level of factorization, so 1 or 2 factorized features, is related to amplitude and latency of each component, and to determine whether there is evidence of markers of configurality and multiple sources of configurality through mapping of these findings to our previous violations of the GRT constructs. So relating back to the theoretical question, is there more than one source of configurality in the trace? So participants are recruited 23, but I have very, very strict inclusion criteria. So I ended up with 16 in the final study. So my participants had to be right-handed, non-smokers, no caffeine, clean hair, couldn't run or be late for the study because you can't be sweaty. And they couldn't be on any form of psychoactive medication, couldn't have any history of headaches, migraines, or history of epilepsy or any kind of brain injury, which would affect the EEG recording. Reasons participants were excluded at later stages included poor task accuracy, poor impedance values, or poor quality data because so many artefacts had to be removed that we ended up with 2 key trials. And I never included partial data, so if there wasn't enough for one condition in the study, the participant data was removed from the whole thing.
Why did you choose them to be caffeine withdrawal?
I was recommended by Sam Boyd. She said that caffeine can affect the waveforms, I think, in the brain if you've had it very recently. So I said that they couldn't have had it in the previous 3 hours to show up to the study.
So interesting, I know of labs where they do the exact opposite, where they give them caffeine just before the experiment because it makes the waves better. But I can imagine that you've got noise if it is for one participant and not for the other. But some labs actually do it.
Yeah, I guess that's that you need to anticipate that everyone's will be the same level. So that's why, I mean, I took their advice on it and just used the same exclusion criterion questionnaire they used from the IDEA lab for my participants, and it was probably overly strict. I also looked at sleep as well. If they didn't have a good night's sleep the night before, there's a risk they're going to become very drowsy during the study, and drowsy, the wave frequency is too low for the study and they'll keep dropping off to sleep. So yeah, if they admitted that early on, not today, but I didn't have that luckily. I did have one person that was late and ran all the way there and then couldn't take part because sweat is an artifact in EEG as well. So it's unfortunate. In terms of design, it was a repeated measures design with orientation of faces, either upright or inverted, and factorization, so typical face, just eyes factorized, just mouth factorized, or both, so 8 different conditions. Each participant completed 1,920 trials, 240 so that was split into 16 blocks of 120, so each block was about 4 minutes, and participants had to keep very, very still during that time, very relaxed, and then had to ensure they took breaks between each one, took time to fidget, cough, have water and everything they needed in between. It's very, I guess participants, it's very enduring. There's a lot to consider and it's very hard going for them, I guess, being in the lab situation. So thank you to everyone who took part here.
So which component, before you conducted this study, which component do you anticipate would be a good candidate for the marker based on your previous empirical finding or your theory?
Well, given that we are looking for both conceptual and decisional, I was quite interested to see what was going to happen at this later component, the P through B, because often, not necessarily with these factorization studies, but often with face processing studies, they just look in a very narrow window and they never get to a component that late. They'll just be looking at M170, P1, M170, P2, and then just stop, cut their window, and they don't look beyond, they only look in the occipital temporal areas and have a very narrow kind of approach. So I was interested really to see what we would get if we looked at that as well.
So that narrow window, is that because typically by that time participants has already made their responses?
No, it's just because of the vast amount of literature that suggests the M170 is the marker of face processing, so they're only looking in the sites, because P1 and P2 are listed in the same electrodes as that whole component. They examine those as well, so they'll look only at those clusters of electrodes, and beyond P2 in those electrodes you're not going to see anything, because the processing will then move to a different area of the brain. So they considered, because they have a view that configurality is perceptual, we should only look at the perceptual area.
I've got a question.
Yeah.
In this experiment then, it's the same task as the first experiment that you described.
No, the task is different. I think that's the task is my next slide. So the addition to this study was because I read this paper that said that the P1 effects were an artifact of coarse stimulus control. I spoke to Eric, and he helped me complete a fast Fourier transform to equate spatial frequencies across my stimuli and made them very well controlled for the low-level properties. So that's why I don't know if it's very well on this, but they've got like a filter. You can see this sort of like filtering across them. You don't really see any high contrast edges where the features have been cut out or anything like that. So it's the same. They are the same stimuli, but they've had an extra control added in. But the task itself is different. So in the task, before they saw a face, they made 2 responses. Here, it's not that I don't think it's possible, but given that this was my first attempt at this study, I wasn't sure whether 2 responses and how to calculate the ERP, like how it's going to work. I think I need a bit more experience. I think it's too hard going. A GRT study itself takes, I think my factory illusion one took about 3 hours, and that's just not possible to get both kinds of data from a single experiment. It might be possible to do a subsection in an ERP paradigm, but again, I'm not sure what might be associated with 2 button presses. So if there's artifacts for button presses, will I lose information about the second button press because there is movement involved, which will affect the EEG recording? Will I always have problems looking at the second response and things like that? So I need to take a bit of advice on that one to see whether I'll be matched. So in this study, participants saw a blank screen, a fixation cross that was presented for a random interval between 500 and 900 milliseconds, which is really important, so there isn't like an anticipatory response, and you'll see that in ERPs if people are anticipating the time at which a face will be shown. They saw a face for 100 milliseconds that was either presented upright or inverted, and they saw a blank screen for a second, which was their response window, and they had to respond whether the face was upright or inverted. So it was a very easy task, so my participants were excluded for not doing well enough on the task, being tired, that sort of thing. Is quite long, getting flustered or just being bored, and they wanted the money. And in terms of recording, we recorded from 60 channels on Scout, and we sampled every 2 milliseconds. We filtered out waveforms that we knew weren't going to be associated with brain activity, so that might have been other signals that were picked up from electrical sources in the room and other things. We kept our impedances very low because we wanted to have good quality data, and we monitored the eye movements using electrodes above and below the right eye. The pre-processing stage, the cleanup, if there were any electrodes in particular that were noisy, so maybe the connection to the scalp wasn't so good after a period of time, we then excluded it from the analysis. We filtered our data to remove waveforms that we knew would be associated with things that weren't to do with the task, so like drowsiness, where people are starting to nod off, because I sat them in the dark as well, so there were occasions where that happened. I've shown you how blinks affect the recording, so we had a blink correction algorithm. We correct the recording for the pre-stimulus activity, so for 300 milliseconds preceding sitting face, correct it for your sort of baseline brain activity for that. And we only look at correct trials in an interval for 300 seconds before we're only using correct trials, and because I've explained we use a lot of trials through artifacts, the first thing we had to do was ensure that we weren't losing too many trials from very particular conditions. We just checked that we have roughly equal numbers across all conditions across participants. So our cut-off sort of minimum is to have 40 trials per condition for each participant, and that again that was suggested by Sam. And we had just over half the data, but we got participants to complete a lot of trials, so we knew we'd have enough at the end. And then we compute, here is a plot actually of the grand average of every electrode that was recorded from and the ERP associated with it in that time window we were interested in. And from that we calculate the global field power, which is an estimate of the standard deviation across at every time point in our time window. And from the global field power, which is at the top there, you can see there are 4 sort of peaks of activity across time, which then correspond to our 4 components we were interested in. One at roughly 100 milliseconds, one around the N170 time, one at P2, and one later, which is P3 component, P3B component. So in order to get all the information we needed for analysis, we used this plot to identify the electrodes of maximum amplitude at each of these peaks of activity.
How many peaks is there?
4. So these ones are just very close together. So that's P1 and that's N170, and they're all positive because they're standard deviations. In this case, but we can see from the activity here, you'll get the opposite potential depending on the area of the brain. So if it's a posterior component, you'll get that's negative, you'll get positive potentials in front of the brain. So that's why we call this a butterfly plot. So it's sort of symmetrical, but it's a bit lopsided depending on where the component is. So we take the electrode of maximum amplitude for that component of interest, find its peak, and then create a window to examine the cut about the top third of the peak. So for the first 3, because they're quite brief visual components, that tends to be a window of about 40 milliseconds, but for the P3B, which is a lot broader, it's a larger window. So for peak detection, we picked not only the one electrode that had maximum amplitude, we picked the 3 that did, and then we selected the other electrodes that correspond to symmetry to compare between hemispheres. So we did this for each component. So it happens that P1 and P2 use the same electrode clusters, but N170 and P3B, different electrodes were chosen. So any circle that has a little name in it is one that we recorded from, but we only analysed using the ones that are coloured in grey. These topographical maps here just show the activity across the scalp. So this is the only sort of spatial evidence I have from this study. Yes. For each of those centres of those peak windows that we've selected. So for P1, N170, P2, and P3B. So you can see in the one on the far right, we're interested in a positive component here, but we can see 2 locations of positive activity. So we know that the P3B is only elicited in the parietal area of the brain, so we know we're looking at that sort of area and posterior sites, not the frontal area. That's a different component of the P3. So it's a different subcomponent of the P3 that's not related to what we were interested in with the study. So that kind of guided which electrode of maximum amplitude to look for that particular one. Okay, so in terms of peak detection, we then take the window we've defined for each of those electrodes we've selected that we're interested in. For each participant, we then look in the window and select the maximum amplitude and the corresponding latency for every electrode of interest, for every component window of interest, and for every participant. But rather than looking at an electrode by electrode basis, because our spatial resolution isn't rate. We averaged across clusters, so the clusters would be by hemisphere, right compared to left, or right, left and midline. And we computed repeated measures and overs for hemisphere orientation and condition across amplitude and latency of each of these components. So this is just summarising where our significant effects are. I'm not going into them in more detail. So the first thing, no significant effects of P1, so that supports previous findings. In terms of effects of orientation, I've plotted the early components using the P08 electrode. So even though the analysis was done on an average across electrodes, when you plot ERP, you show an example of real data. So this is just one electrode that happened to be in all three of those clusters that we used in the analysis. So it's not necessarily the best example for each component. It's not necessarily the maximum, the electrode that shows the maximum amplitude, but it shows the general pattern in that area of the brain. So this is in the right hemisphere. So, yeah. There was main effects of orientation for amplitude of the N117 with inverted faces eliciting a greater amplitude, but also inverted faces eliciting increased latency of the N170, and for P2, upright faces elicited a larger amplitude. Did a similar thing for the P3B. This time I've chosen the CPZ electrode, which is in the central parietal area, as an example of an ERP. There was main effects for orientation for amplitude here as well, with inverted faces eliciting a larger amplitude. And there was an interaction of hemisphere and condition at N170. So level of factorization was significant in the right hemisphere but not the left hemisphere, and you can see there is an ordering by factorization with a reduction in amplitude with level of factorization. So there's a difference between this one and this one, this one and this one. Okay. I haven't put the stats on for the hemisphere effects because we weren't, that wasn't our primary interest, but we did replicate previous findings that found larger amplitudes for the M170 in the right hemisphere. The P2 peaks were faster in the right hemisphere, P2, and for the P3B, the largest amplitudes were on the midline compared to the other two hemispheres. So in summary, these results, there were effects of factorization on the M117 in the right hemisphere. There were effects of inversion on the M170 and P2 for the early visual components, and an inversion effect at P3B, which is the later component. And these two effects of inversion are distinct, and they're from different sources. They're located in different areas of the brain. The inversion effects are qualitatively similar across M170 and P2, because it's almost like an echo of the pattern across these two electrodes. I haven't gone into sort of the stats of how you would identify whether it's almost a carryover from M170 and P2, that there is a difference. But the important thing is that at P3B is a different location, and it's from the previous component we've looked at. It's a swapping of which orientation is showing the larger amplitude. We found reduced amplitude and factorization in the right hemisphere at M170, which is consistent with previous findings of factorization reducing amplitude at M170. We didn't find an interaction of orientation and factorization at M170, which you might predict given the phenomenology of the illusion that you'd expect to see some sort of interaction between the two, but that's not particularly striking because overall we didn't really find any main effects of factorization. And I haven't really looked into this too much, but I do wonder whether these if the low-level visual controls actually is not just P1 that it's important for, and maybe it has carried over into these other components as well. But it's meant that we're not finding much of an effect of this thing like that. So we found these three sorts of key findings in the ERP. So two types of inversion effects on one of the level of factorizations. And now thinking back to to the 3 effects we found in our GRT study. In the GRT study, we found the type of violation differed by, or in the type of single-line study. So when we found violations of perceptual separability, of perceptual constructs for the upright faces, and a violation of decisional separability for the inverted faces predominantly. So if we were looking to map it to our ERP findings, we'd be looking for inversion effects. Well, M170 and P2 are perceptual components, P3B is not. So it might be that we're looking to map these violations of PS very earlier in the time course, which might arise as these inversion effects we see at M170 and P2, and the violation of DS later at the P3B in a different location. And in terms of the violation of PI, violations of PI that were found across upright and inverted conditions, well, we did have evidence in our ERP study suggesting that there was an effect of factorisation at N170 in the right hemisphere, so maybe we should be looking at the N170 for evidence for these correlations there. So key findings, no P1 effects, which replicates the previous findings for lower level properties driving the face-specific effects in previous studies. We found effects of P3B, which suggests evidence for a decisional component when we use this data-driven method, and that's a really important point because other studies don't necessarily set up their methodology in this way. They may have predefined electrodes they're going to look at based on previous literature, or predefined time windows based on previous literature. They'll look at the same, all components from the same electrodes, so they're not opening themselves up to look for anything other than perceptual effects. So when we do open up and look to see what the data is going to provide to us, there's evidence that there's something related to the task and inversion effects that's not happening in those same areas of the brain. The effects of factorisation and inversion are independent, which might be surprising given the phenomenology of the illusion, which we talked about a little bit. And we found a sort of correspondence between the evidence we found in the previous study and our findings here. And something like this has been attempted before, a mapping between the composite face effect in the GRT paradigm and an ERP study. But they didn't design the task in quite the right way to be able to find evidence for decisional effects. So they reported they didn't find any evidence for decisional effects from this task at the P3B. But since there's been criticism saying that they've amended their task to use this complete design where you have all the different possible levels, so the complete factorial design, like I described before, then that would have been the proper test to find out if they existed for that particular task. So in terms of where this is going, we are now exploring this task with a post-diagnostic individual. I've only run one session so far, so this is just preliminary data and don't have any stats in it yet. So I've just plotted their results against the control data from the study. And the first thing you can see is that the ERP is very attenuated in terms of amplitude, which is normal for someone who has suffered brain injury. And again, this is the P08 electrode, just looking at the early components. And it's interesting to see that even though the amplitudes are smaller in magnitude, reduced, there's still a difference between the upright and inverted conditions. So I'm not really sure what that means yet. And it's not to say that they have evidence of a phase effect at M170 because we're not comparing two objects. It's just interesting to see that there might be something residual there that differentiates upright and inverted phase processing. In terms of looking at P3B, well, we're not really sure what that is yet. It looks like it could be a late P3B or something else, so we need more data to identify what that is. But overall, it looks like it's going to be an interesting project, so I'm looking forward to collecting more data and seeing what that might reveal for identifying the sources of the deficit for this particular individual's prosopagnosia. So I'd just like to thank everyone who's contributed towards this task. I've had a lot of help setting up the study and explaining sort of principles of the of many of the ERP components.